Good afternoon, everybody, and welcome to Friday afternoon's lab session of MI212. It's Matthew Riggs, a course instructor for this week. We are going to go through today just some clarifications on the lecture from earlier this week, the Advanced PK/PD Modeling Topics 2 lecture. One other note to point out, if you have all checked the MI212 website, you'll note that there's a new copy of the course book on the site. It now includes the two missing chapters that were not present at the last lecture. Those are the previous two chapters, chapters 4 and 5. Again, I apologize for that. I did it knowingly so that you could get the chapter 6 material in a day's notice of the lecture itself. I had to go back and just coordinate with Mark to get the material for 4 and 5 on the same computer. So anyway, that's all in there now, and so you can refer back easily to, for example, the PK/PD model with tolerance and compare and contrast that to precursor pool models, etc. So again, that is all in there. I wanted to start off today just by going through and clarifying a few points that were brought up at the last lecture that, as I was thinking about, I wanted to add some additional detail to, and a few questions have rolled in the last few days as well. So I'd like to start off by going back to the control stream that we had looked at for the precursor pool model, shown here in the notes. One point of clarification from that. I had mentioned during the lecture that if you put in the dummy compartments within the data set, and let me just find the data file here. We'll go sort of forwards and then backwards. I had mentioned that within that data set, we had the records in here corresponding to EVID2 for compartments 2 and 4, and then the observations in compartment 5. And during which I'd said that if you include these dummy records, then the pred value that you get from NONMEM will be the pred value for these compartments. In fact, what you need to do in order to actually get that back out is you need to tell the control stream that as well. And so if you'll notice in the new control stream here, make the statement that if compartment equals 5, IPRED is equal to A5, and then below that, if compartment equals 2, IPRED is A2, which is the amount in the central compartment for the plasma for PK, divided by that scaling term, or V2. In this case, it's V2 over 1,000 to get the appropriate units. And likewise, for the precursor pool, we make the statement if compartment equals 4, IPRED equals A4. We then tell NONMEM that the prediction is equal to IPRED, and in which case that's going to be different for each of the compartment records, plus an additive error. And so by doing that, and we'll take a look at the actual output here in just a minute, we'll actually get predictions at each of these different compartment records corresponding to that specific compartment. The other thing that we get, because we have included C2, A4, and A5, is we not only get the predictions, but we actually also get the individual predictions for each of those compartments. Now, in this case, one thing to note is that you see here we have IPRED plus error 1. We only have within this data set, we only have observations within one compartment, being compartment 5. If this was a case where we're fitting multiple observations, for example, if we were simultaneously fitting PK observations in compartment 2, what I would also do is I would also include these statements up within the if compartment block. So for example, up here I would have y equals IPRED IPRED plus error 1, and then down in the PK block we'd have a separate error term. So we had a different error for each compartment. Now what I had, I guess I should clarify too, what I had originally in there was I had IPRED equals F within the error compartment. And I thought maybe this is something that's changed in versions of NONMEM, but I thought that would automatically give the predictions for the individual compartments. But I actually went back and looked at the output from that, and it turns out it was just the predictions for compartment 5, regardless of what was on which compartment the data set was referring to. And I think the reason for that too is because I have up here that compartment 5 is the default observation compartment, and so it gave me predictions. Every prediction was referenced back to compartment 5. So again, this does the trick. And I'll show you here in just a second why we would want to do that in the first place. So let me jump over here to SIMI. Hopefully my session is still alive here. Looks like it. And I'll just show you and each of these scripts should be in the zip file that I provided earlier this week. Just take me a second here to resize the windows. And I'm just going to set up the project directory and such here. And I'll show you, I'm going to read in the output table, which is 2par.tab. See if I can make this bigger. There we go. Okay, so what I've done here is I've just read in I've called it fit. I've read in the 2par.tab, which is the output table file from the fit to those data. And we're now looking at just the first 5 records of the data set. And unfortunately, R doesn't do the best job of giving you a even view of the data. But I guess if we look at just the first 3 records of the data here, we can start to get a feel for what we have tabled. So we have, right here we have the different compartments. So we've got compartment 2, compartment 4, and compartment 5. We have the DV value is just here in compartment 5. That's the baseline value for ID1. It's giving us a negligible amount for C2. Should really be 0, but so that's the PK individual prediction. The next column over, the 60.453, is the individual prediction for the precursor pool. The next column over is the individual prediction for the luteinizing hormone. And then, so the one thing to note is that you get this prediction for every single record at every single time. What we've asked for is a different prediction depending back on this compartment record for each IPRED and each PRED. And so you can see at time 0 for compartment 2, the individual prediction and the population prediction are 0 for PK. We get an individual prediction for the precursor pool, and note that that's different than the population prediction for the precursor pool. And also the same for the luteinizing hormone, we get an individual prediction and a population prediction here. So great, who cares? Why do we want that? Well, what this then allows us to do is to go back and plot different things. We may be interested in individual predictions, population predictions, having each of these values by compartment allows us to do some plotting features, and then having each one continuously also gives us some plotting conveniences. So for example, if we wanted to plot A5 versus C2 or A5 and C2 versus time, we can do that because the rows are lined up next to each other, fairly simple. If we wanted to plot prediction or IPRED, we could do something like I've done down at the bottom of the script here. Let me just, somebody asked up here about this GC command. This is a garbage collection. Somebody had fun, I guess, with the name there. It just takes any, with a fresh script, you don't need to do it, but it takes any junk that might be hanging within R and gets rid of it as you start up a new run of a script. So if I had run something before this and I want to make sure there was nothing, this and the remove, nothing in the sort of cache, if you will, or any objects within R, these two commands take care of that. So what we can do then is the code that I've shown down here. If we do a plot of PRED plus IPRED by day, and we condition that on compartment, we can then plot each of these things across time. I'm just going to jump over here and show you what that plot looks like. I believe that's this one here. It's tiny. And so what this does is it gives you all of the plots. You can do it also by individual too, and cut it down even more. But it gives you the individual predictions of PK for each of the individuals. I put in a grouping variable by dose, so you can see by color what the different dose group each individual belonged to. So you can see the individual predictions, the population predictions of the PK, the precursor. Remember we talked about how that precursor built up over time. And that's really what leads to the tolerance development and the rebound at the end. And so you can see that, and then you can see again the individual predictions and the population predictions for the platelets as well. So also within this plotting script, I've shown a way where, if you recall from the course notes, we had the plot of the individuals, where we had the individual data, the observations, the individual predictions, and the population predictions overlaid on one another. I'm not going to go through this whole script, but that's laid out at the beginning of this script here. And again, that was provided in that zip file. Just to run through quickly, essentially what you have to do is stack the data on top of each other, and we create this ident label within the data file. That becomes either the observed value, the predicted value, or the individual predicted value. And then you end up using that ident value as your grouping value within the plot. And you can use the par settings within the XY plot lattice function to make all of the symbols transparent for the predicted values, and then red is the observed value. So that's where you get the red triangles from. And then you do the same thing, but in reverse, to make transparent the line for the observed value, and you include the colors. So the blue in this case would be the individual, the IPRED value, and the green would be the pred value. So again, the script is there. This is more probably along the lines of what you do in the R course to dig more through this. But again, it's there. If you have any questions on it, let me know. Yeah, let me just go back here. There's a question. How do you get different values for individual and population predictions for compartment 4? Yeah, so the different predictions there are probably coming from, I got to go back to the control stream for that. They're not coming, remember the IPRED values are, even those don't include any residual error. The difference between the IPRED and the DV is the residual error. The difference between the PRED and the IPRED is driven by inter-individual variability, so those eta values. So let's go back and look at the control stream. And so we have the eta on the K0 here. And K0 is what's driving the input rate for that precursor pool. And so that's what's allowing for the difference between the individual prediction and the population prediction for the precursor pool. Okay, so again, hopefully that clarified a few things and added some information for the precursor pool models. Next thing, I'd like to go over a couple more things on the transit compartment models, again, to clarify a few points that were brought up at the last lecture. And one of the points that was brought up is, let me just go to the schematic here. We talked about the way of setting this up, where in this particular example, we're looking at this entire box being the sampling compartment, if you will. So this entire box represents, in this case, platelets. And somebody asked a question that they noticed in a different paper, that there was this transit compartment, and then the actual sampling compartment was out here, out beyond the transit compartments, and how that would work compared to this type of parameterization. So what I've done is I've actually gone and pulled a couple of papers that show you the differences here. And before I show the actual papers, what I'll do is maybe give you my explanation of them, and then as we look at the two papers, we can compare and contrast them as well. This is a case here where we're actually looking at the cell maturation and sort of the in a sense, the lifespan of whatever we're measuring. And in that case, you're measuring, in this case, platelets, and you're looking at this K-transit represents the lifespan of how long these cells are going to live for, how long they're going to stay in circulation. In the case where you have a sampling compartment out beyond these transit compartments, that's actually a situation where you're looking at the maturation of almost precursors, if you will, before they become that actual active cell. So you may have something coming from bone marrow slowly maturing into, say, some type of immune cell. And so you'd be looking at the delay in that maturation from your either stimulation or inhibition before it becomes a fully active cell. And so again, the difference there is, are you looking at the lifespan or the maturation life of the cell that you're actually measuring, or are you just trying to delay the length of time before that cell actually occurs? And so let me pull up a couple of papers just to show that here. And so here's the first example. Let me expand this. And these are both references that are within the class notes. This is a lifespan model where they were looking at, I believe it was red blood cells. Yeah, red blood cells. And so, again, this box here represents the entirety of the measured red blood cell. And what you get out of this is these KLSs then represent, when you take the 1 over KLS, or in this case it would be 4 over KLS, you're getting the expected lifespan of the red blood cell. In the other example, shown here, where again, this is a myelosuppressive drug. And so what it's doing is it's actually killing these progenitor cells before they mature into the circulating, whichever cell they're looking at here, maybe a white blood cell, a neutrophil cell. And so this, whereas over in this model where the 4 over KLS represented the lifespan of a red blood cell, this 4 over KTR represents the maturation time of one of these progenitor cells becoming the neutrophil cell. So this NTT isn't the neutrophil expected life. Again, it's the sort of average time, if you will, that it takes a cell to become a neutrophil. So a little bit of a nuance there in how you interpret these models. And again, it's probably worthwhile thinking about the pharmacology of the drug. In this case, you know that you're affecting something far beyond where you're going to see the effect, and so really you're looking to delay you're looking to delay when you're actually going to see the effect. Here you're looking at something with a very long lifespan, and so it's going to take a while before those younger cells kind of mature on through, and that effect sort of propagates on through this lifespan compartment. So different ways of setting up the model, different ways of using the model, and I just wanted to clarify that. I guess one other point I can make, and I'll come back to it too in a second here. I had said before that when you look at the this mean transit time here and over here, sort of the mean lifespan being the number of compartments, and I had misspoke when I said the n+1 over k transit. That's actually only applicable to the way that we generally parameterize the transit compartment for absorption. When we're dealing with these sort of PD models, the best way to think of it is it's the number of these KLS or K transit parameters divided by K transit gives you the mean transit time or the mean lifespan of that particular cell or cascade system. And I'll just show you the one last paper here to kind of clarify that. The way that the transits for, and this was actually another point I think that one of the attendees had brought up last time, the way that these transit compartments are typically set up is there's an A0 compartment as well. So that's where the n+1 comes from. So again, I had it right in the control stream, but I think I had it incorrect in the notes, and hopefully I've gone and fixed that. Okay, I see a comment here that they don't see the Gupta paper within the reference. I'll go ahead and I'll add that. I'll add that to the notes. And so the next time you get a load of the notes, that reference will appear. Okay, so again, the K transit being the number of compartments or the number of these KTRs that you have within the model, divided by the MRT, or vice versa. You can figure out the MRT by doing 3 over K TR. I don't think anything else has changed within this. So I think previously I had noted that this was actually right here in the notes, that this was n+1. Within the physical control file on SIMI, I hadn't put this note in there, and it was correct previously, and all the data and everything were simulated correctly. It was just I may have put it up here as well, as I added notes to the control stream for the course itself. Okay, I think the transit model for oral absorption we had just started to get into during the end of the lecture there. The one thing that we didn't get to go over was the use of this transit compartment model more in the sense of viewing it in terms of a gamma distribution where the parameters that define a transit compartment can actually be used as estimated values within this gamma distribution. So you can actually fit and estimate the appropriate number of compartments n and this k transit time. And what that does is it gives you, I've shown a few scenarios here when you vary n but keep k transit the same. This is the amount of dose that's in that final sort of transit compartment, so ready to be absorbed over time. And so you can see as you increase n, your mean transit time increases, and you can shift both down and over the amount of drug that's about to be absorbed. So typically this would be the amount in the gut if there was no transit. Likewise, if you maintain the number of compartments but change the rate within drug is moving across those compartments, you can shift this distribution over time out to lengthen the delay. So again, you can lengthen the delay either by changing the number of compartments, or you can lengthen it by changing KTR. When you estimate both of these together, you can imagine that you can fit just about any distribution that the data dictate. So this is a useful function to do. I've used this once or twice, and it does tend to increase your computation time. It's a pretty computationally intensive model to fit. I've given an example here of that control stream. One thing to note is that you need, and I mentioned this down in the points to consider, you need to use, number one, the time after dose to drive the absorption. If you use time with a NONMEM, and you can imagine after the 10th or 11th dose, your time is much greater than what the actual time is coming out from this scale here. So you need to parameterize this thing so that it's actually ticking off of the time after dose rather than the running time with a NONMEM if you're doing multiple dosing. The other thing being is that there can't be any drug left in this transit compartment when your next dose comes through, because the way that you parameterize it and the way that you set it is that everything's cleared when the next dose comes through. So you can imagine a case here where if you have every 8-hour dosing and this is your estimate, you're gonna run afoul. So you want to be mindful of that. Generally, with most of the dosing we do, this is a fair assumption, but you always want to be conscious of that. I'm just looking at a few questions here. Yeah, here's a question here. If we use the analytical solution, it's tricky to introduce multiple doses. I've given the code. This is actually the Carlson's group at Uppsala had kind of solved this out. What you end up doing is fooling around with the time variables within NONMEM to determine the time of the dose based on when the amount is greater than 0. You then use that to kind of calculate a running time after dose within NONMEM. And you end up then feeding that sort of time and T-dose. T in NONMEM is the actual differential time. So that's the true time within NONMEM. And so the code for all that is down here. And again, the trick is that you got to make sure that all of the drug is out of that that delay transit system before the next dose is given. So if you run some diagnostics on that, it can be as simple as this was all set up in an Excel spreadsheet. Just looking at this to see, you could put your parameter in, your N and your K transit, and you could say, oh gosh, I've still got some dose in there when I'm introducing the next dose. This isn't going to work for me. If this doesn't work, you can't use it. You'll have to go back to sort of defining a number of transit compartments and just continue on with your dosing that way, unfortunately. So really, there's no way to change that. If drug's still there, drug's still there. You can't avoid it other than to change the dosage form of the drug. So, which usually isn't warranted just because your model doesn't work. But I'll leave that there. Okay, actually, as I was speaking, I was reminded of another question that I'd gotten earlier today regarding these transit compartments and the precursor pools. The lags that we're seeing in the pharmacodynamic model, so the lags that you see within the pharmacokinetic model generally are lags that occur within a dosing interval. The lags that we see and the tolerances and everything else that we see due to or that we're trying to describe by these pharmacodynamic models, they do not have to exist or occur within a single dosing interval. These things can take hours to days to weeks to show themselves in full light, and really what determines that or how we estimate that is by estimating different values of, for example, the K transit. So again, the longer that is, the longer it takes for this effect to propagate through all of the transits or the chain here. And so this type of a model can be used to describe biology and pharmacology that take, again, days, hours, weeks, months, whatever the case may be, to be able to describe that. And so when we go to the problem that was put forward for this week, let me just jump down to that. Make a note. We'll stop there with the actual lecture notes. I don't want to go any further with that. We'll cover the lifespan models at the beginning of the next lecture. It's a fairly small section, and then move into the multiple endpoint models that was scheduled for next week. So the problem itself that was assigned for this week, and again, we'll start to go over it here, and then we can continue on with it next Friday if there's some more questions. I do notice a couple of other questions have rolled in. Let me just take a quick look at those before we get into this. Yeah, so there's a comment here regarding the use of that gamma distribution, that somebody's had success doing it in Win nonlin, superimposing the doses. Just not sure how to do this in NONMEM. Certainly that would be the way to do it. I'm not sure that it's possible to do in NONMEM either. Ideally that would be... how to do it would be to somehow let NONMEM know to just continue superpositioning those doses. But the way that it's set up right now, it won't do that, the way that the model's coded. not sure that anyone's figured out a trick to get that to work yet. Okay, so getting back to the problem statement for this week. Really, it was intended to kind of show a little bit of a twist of both a precursor pool model and a lifespan model. Taking the platelets example that we were looking at for the example for the lifespan models, and adding to it a precursor of the megakaryocytes. Megakaryocytes are those cells that platelets are derived from. They essentially shed off of the megakaryocytes and become platelets. So I still need to fix this down here. So this should just be N over KTR. The trick here, though, is if you look at the data, the actual plotted data, you'll notice that we get an increase in platelets over time, and then once therapy is discontinued, shown here by the dashed line, there's again a gradual decline back towards baseline, but you don't see a rebound. So why is that? So this is a question that, if you look at the difference between this particular model where the drug is stimulating the production of the precursors, the megakaryocytes, and then those are then producing the platelets. If you recall, it's when we affect this K-in term that we actually get that tolerance and rebound to occur. So in this case, the drug is actually working on stimulating the precursor rather than affecting the transition from the precursor to the outcome response here, in this case, the platelets. And so again, that's the reason that you're in a sense using a precursor pool, but you're not using it in the classical sense where you're then imposing some form of rebound or tolerance occurring. So it's a little bit of a play off there. And again, to the point that these effects don't need to occur within a dosing interval. So what I've shown here on the top panel is that when you give this drug, it achieves steady state. These are the trough concentrations within a matter of a day or two. Yet, if you look at the pharmacodynamic response, that's still continuing to accumulate 2-3 weeks after giving the drug. And the way that you're able to account for that is by including that precursor and those transit compartments within the model. And so that's sort of the setup, if you will, for the problem for this week. What I'll do is I'll start to show you some of the. We'll go back to Simi here. It's probably kicked me off at this point. Let's see. Maybe not. Okay, and what I'll do is I'll start to kind of show you what the control stream looks like. I won't load these files up yet. Maybe I'll give you a crack at trying to recreate them after you get a little bit of a sneak look at them here. And then we'll go through some of the diagnostics and such next week, next Friday. So again, this is the sort of the solution, if you will, for this, or a solution. Looking first at the model statement for this for this particular problem. We have kind of the classic setup here where we've got the oral dosing into the gut compartment, the central compartment for the observed PK, peripheral compartment, and then what we have is a compartment for megakaryocytes, which is the platelet precursor pool. And then we have sort of the three compartments here. Again, if you were doing this in a real life scenario, you'd probably want to look at more than three compartments, at least test that. And so, just for ease of example here and runtime and such, we're looking at just the three compartments. So we have those laid out here. We're reading in the PK estimates from a prior fit, so it's a sequential type analysis. And then we are looking at things, we're parameterizing it in terms of those lifespans. So we have sort of the megakaryocyte, or the M, mean residence time, the platelet MRT, and then we've got our Emax, our EC50, for the pharmacologic effect. We rescale these sort of mean lifespans back to our first order rate constants. As we saw before, we only have one compartment for the megakaryocytes, and so it's 1 over that lifespan parameter. And then for the platelets, we have 3 transit compartments, and so it's 3 over the lifespan estimate for platelets. So one of the things that you'll probably notice that it's you have to make some assumptions here because you don't have observations of the megakaryocytes. So we assume just an initial relative value of 1 for that compartment. This would be a case where if for some reason you can measure whatever this precursor was, you could certainly fit that value as well. So we initialize the megakaryocytes at that value. We had mentioned before this little trick of initializing each of the individual life bins, if you will, of the platelet compartments at 1. And then down in the error block, we add those together. We multiply them by the initial estimate for platelets and divide that by the number of transit compartments. And then the differentials are, kind of as expected. We have an input rate for the megakaryocytes. We're stimulating that with this drug effect E. E is the sigmoidal Emax up here. And then the same code that we had looked at before for the transit compartments. The nice thing about this is that when you get the estimates back out, we've put in here initial estimates of 108 hours for the megakaryocytes and 240 hours for the platelets. You then have values that you can go back once you've estimated the fit to the data. You can then go back and compare to literature values for what these particular cells are expected to have for lifespans. And it turns out that a megakaryocyte, I think, lives between 4 and 5 days, and a platelet is somewhere around 10 days. And so, that's the value I use for the simulation. But you can actually compare then your fit to real data back to what's expected. And so that, to me, is one of the advantages of this type of model and this type of a parameterization, is you can actually go back and compare it to real biology and physiology. So again, I think that's about it for the problem. Again, what I'm going to do is kind of close this out now. I guess you can cheat and look back at the recording, but I encourage everybody to go back and just take a look and a thought at how you would set up this particular problem and how you might write their control stream for it. I guess one other point to make is when you look at the data file for this, and I think I'd mentioned this before, it doesn't really matter where you put the observation as long as you tell NONMEM within the control stream where it's at. So let me actually just go back to that control stream just to show you. So what we've done is we've made this term EFF, the effect. We've set it equal to the sum of the compartments. And then in the error block, if we were fitting both PK and PD, we would use this type flag. Because we're only fitting PD, there's only one observation within the data set, and so it's going to look for that. Whenever it sees an observation, it's going to compare it back to this EFF value. You notice we don't have to put it in any given compartment because it's not any one of the compartments, it's actually a sum across compartments. And so as long as you duly note it within the control stream, and in this case, since we only have one set of observations, if you will, it's much easier to handle. Otherwise, what we would do is we take advantage of this type flag, which is within the data set, and I've kind of sort of given an example here of how you would use it within the control stream as well. And again, that's differentiated here by the those observations. Let me see. Yeah, so this is a data set that was originally set up with the PK values in it as well. So here you can see that it's a commented out value, so NONMEM doesn't ever see it within the fit. But there was a PK observation here. It was a type 0, and it was also in compartment 2. So if we were to be simultaneously fitting the data, what we would do is we wouldn't have these C's here. We would allow NONMEM to see both of the PK and the PD data, and then we would use that type flagging within the control stream to differentiate the two. So again, I think that's about it for that. Let me go and check the questions here. Yeah, so it's a matter of semantics here. So rather than a precursor pool, it's more of a combination transit model. And yeah, in a sense it is, except that this truly is a precursor of these later cells. It's not a precursor pool, again, in the classic sense of the Sharma paper, where they're affecting this one term here, and so you develop the tolerance and rebound. So it's again, a precursor in a sense, but not a precursor in the tolerance and rebound sense. Okay, question here. On the differential here for dA dt4, where did that come from? Okay, it's probably the K in here. A little bit of a trick here is that let me pull back the because this megakaryocyte compartment is started with an initial condition of 1, you can more or less say K pre in equals Kn. So you can rewrite it so that Kn, this is Kn and this is Kn. So again, it's one of the simplifications, I guess, if you will, because you don't actually know what this initial condition is. And so you set it to a relative value of 1. That allows you to, and I've shown that here, K pre-in is equal to Kn times meg0. Meg0 is 1. And so you get the Kn on both sides. Looks a little funny, but it's just a mathematical simplification. So another question, I still don't understand why we decided to use a combination of the two models. Really, this is a matter of you kind of understand the biology and the pharmacology and what you want to get out of the modeling. Certainly you can fit this with something. You probably could get away with fitting it with just a form of a transit compartment, but what this gives you by combining and estimating this precursor of megakaryocytes plus your platelet model is it gives you separate estimates of how long you think megakaryocytes are going to live for and how long you think platelets are going to live for. And then you can start to do things like if you understand different disease states. So there are people that have deficiencies. So thrombocytopenia can be caused by different factors. It can be caused by chemotherapy. It can be caused by people that have autoimmune diseases, etc. And so then you can start to affect different points of this model. And so, for example, if you're dealing with a population that has an autoimmune disease that may be clearing megakaryocytes before they become platelets, you could have that disease influence this removal rate. If it's a disease that's being caused by chemotherapy, that may be coming back here, similar to that other model I showed you with the myelosuppression. And so the more physiologically real that the model is that you develop, the more different types of conditions and the more you can understand the system beyond just fitting the one set of data that you have in hand. I think that's an important point of, as you get into these more and more mechanistic, if you will, PD models, that you can get into, I think, broader applications of them. And the point too, if you affect this transition from the megakaryocytes to the platelets, you're going to impose tolerance and rebound. By affecting the input rate, you impose a delay, but you do not impose tolerance and rebound. Control stream for this has not been posted yet. This is the problem. So again, if you guys want to take a crack at it, and then we'll review it again next Friday, and then I'll post the file up at that point. So yeah, the DV in the data set represents this entirety of the rectangle here. So the sum of each of the individual transit compartments are the total number of platelets. And I guess another point too is, and just to clarify too, we do not in this case have observations for megakaryocytes. That's why we had to assume just an initial relative value of 1. If we had that, then that would be great. That would give us that much more understanding of the system, but in this case we do not. So it looks as though we're at the 3 o'clock hour here. So I think we've gone through hopefully some good amount of material here to help clarify some of the questions that have arisen from the lecture. Better set up for the problem itself. Hopefully I was able to clarify sort of the thinking behind that and why I gave you that particular example to sort of start to pull all of these pieces together. If there are any additional questions, please use the forum to post those, and I'll get back to you as soon as possible. Just a reminder again, next week we here on the East Coast of the US are going through our fallback to Eastern Standard Time this Saturday into Sunday. So class time will be adjusted accordingly next week. So please just check your own local times to coordinate that. Thank you again, and have a great weekend.